Why, hello there, folks. You are tuning in to another Mr. Carbonaro vodcast. Thank you very much. So you're watching the optimization vodcast. I'm probably going to put up two. This one deals with volume, and then I'll do one that deals with cost and profit. So here we go. We're going to start with this one. This is number 10 on the review worksheet. Determine the dimensions of a rectangular solid with the square base of maximum volume if its surface area is 385 square inches. Okay, so there are 5 steps to doing optimization problems. Okay, 5 steps that you want to follow. Step 1 is you want to label and visualize the problem. Okay, label and visualize what this problem is asking. For example, we're dealing with a rectangular solid with a square base. So a rectangular solid would look something like this. Obviously, I am a fantastic artist, and this is perfect. So there's your rectangular solid. It has a square base, so we have a base down on the bottom here. Alright, draw my little dashed lines to indicate that we have. Okay, it's a three-dimensional picture. Square base means that they're equal lengths. So if, let's say, this were x, this would then be x. Okay, they're equal. So if that were 2, that would be 2. You know, whatever. And then obviously there's a height because it's a rectangular solid. So I'm going to call that y. I know some of you call that h for height. You know, whatever. I'm weird, so that's what I decided to do. All right. So now you're visualizing and you're kind of labeling. You're saying, okay, 2 of the sides or of the base, the sides are called x, and the height is called y. Like, you need to make sure that those things are specified in the problem, especially when you're doing problems that say, you know, the sum of the first number times twice of the second number, you know, all that stuff. You got to indicate which one's the first number, which one's the second number, so on and so forth. Okay, all right. Step 2, we need to identify the primary equation and the secondary equation. So let me write that down. Primary and secondary. Okay. Now here are the rules for finding your primary and your secondary equation. Your primary equation will always be the thing being minimized or maximized. Alright, so when you read the problem, it says, determine the dimensions of a rectangular solid with a square base of maximum volume. Let me underline that. Alright, that means we need to maximize our volume. So that immediately is our primary equation. Our volume of a rectangular solid is length times width times height. Now you in step 1 labeled what length and width and height are. So now when we multiply them out, length times width times height, bam, there's your volume. Now, our secondary equation is the other thing in the problem, where it says if its surface area is 385 square inches. So 385 is our surface area. And now we need to come up with what the surface area is of this figure here. Surface area is the area, the sum of all the areas of all the faces of the solid. So we look and we say, okay, we have the base down on the bottom. The area of that base would be x squared. All right. The area of the top base would again be x squared. The area of the right face would be x times y. Front face would be xy, back or left face would be xy, and back face would be xy. Combine like terms. We get 385 equals 2x squared plus 4xy. Alright? So there's your secondary equation. Now the purpose of having the secondary equation is to eliminate one of the variables from the primary equation so we can maximize it, because you don't want to be taking derivative of something with 2 variables. Right? It gets sloppy. So what we do is, I'm going to come up here, this is step 3. Step 3 tells us to make our secondary equation in terms of one variable and plug it in to our primary. So I'm going to solve for y because it's a lot easier to solve for y in this case. You could solve for x, I'm going to choose to do y. So we subtract 2x squared to both sides. And divide by 4x. Alright, and reduce whatever I need to reduce. Negative x over 2 plus 385 over 4x. Okay, there's my y. I'm going to take this, plug it into my primary. So volume equals x squared times negative x over 2 plus 385 over 4x. Distribute. I get volume equals negative 1/2 x cubed plus 385 over 4x. I'm just writing it like that to make it a little bit easier for myself. Alright. Now, we need to now take the derivative of our volume and maximize it, essentially. I'm going to erase all of this work here and just put what the volume is. Okay. So that's the result of step 3. Now, we're going to do step 4, actually. Step 4 is determine the volume, or the domain. Okay? Our domain for this problem is something should be glaring at you. We're dealing with lengths and widths and heights. Alright, so we cannot have any kind of value less than or equal to 0. Okay, it has to be greater than 0. So our domain is greater than 0. Alright? And any problem that we're dealing with this when you get to step 4, just remember, just think what can't x be, logically what can't x be, and then you'd be good. Step 5. Step 5 is maximize the primary equation. So that means take the derivative. So when I take derivative, I also set it equal to 0. So I get negative 3/2 x squared plus 385 over 4. Alright. I solve for x here. I get x squared equals 64.166. If you're confused on how I did that, I subtracted 385 over 4, then multiplied by negative 2/3, the reciprocal. Alright, I take the square root, make this 8.01. Alright, now it is plus or minus 8.01, but again, that's why we did this domain. It has to be positive number, so we can get rid of that negative solution. Now, we need to check that this is a maximum, so we need to set up our intervals. Our intervals are 0 to 8.01, 8.01 to infinity. Alright, take a point in each, test it in the derivative, I plug it in. When I plug 1 in, I get a positive solution. When I plug in 9, I get a negative solution. So it goes from increasing to decreasing, which means that 8.01 is a maximum. So x equals 8.01 is a max, which is exactly what you want. Which means now we need to figure out what y is, because remember, the problem doesn't say what's x, it says determine the dimensions. Okay? So we need to plug 8.01 in for x into where? Into our secondary equation. Our secondary equation here will give us what y is after we plug it in. When you do this, do a little bit of calculations. Remember my calculator noises, beep, boop, bop, boppy, bop, and you get 8.01. Right? Our dimensions that will maximize the volume with a surface area of 385 is 8.01 and 8.01. Alright? That would be how you do the optimization problem dealing with solids, volume, surface areas, and all that good stuff. Alright. Thank you very much for watching, and I hope this helps. Peace!